All right, let's wrap up with a couple of theorems and examples. So let's look at this theorem. So if a and b and c are positive integers such that the GCD of a and b is 1, so they're relatively prime, and a divides in bc, then a is going to divide in c. Okay, so basically this says that if a doesn't divide into b because they're relatively prime, and a divides into this product, then a has to divide into c. Okay, so let's look at the proof here. So if the GCD, let me pick a different color. Can't see it very well. So if the GCD of a b equals 1, by the last sort of theorem example with the Bezout coefficient, I know that I can write the GCD of 1 as a linear combination SA plus TB. So number times A plus a number times B. All right. So this is our first premise. Our second premise is that A divides into BC. So if A divides into BC, I know that I can write BC as A times an integer. So K is an integer. So this comes from the definition of the divisibility which we saw in the first section of this chapter. All right, so now I'm going to multiply the first equation by C. So I'm going to multiply everything by C here. I'm going to get C equals CSA plus TBC. Okay, so let's look at each of these. Okay, so this right here, C times S times A, I know that A divides into CSA because it has this factor of A. Okay, so A is going to divide in this product because it has a factor of A in it. I know that A is going to divide into TBC because I know A divides into BC, so A is going to divide into an integer times BC. Right? So I also know that if A divides into two numbers, it's going to divide into the sum of those two numbers. Okay, again, this is one of the theorems from the previous sections. Okay, all right. So because A divides into this side of the equation, then that means that A is going to divide into that side of the equation, the same because it's the same value. Yeah. So that constitutes the proof to this theorem. All right, so let's look at this next example, which has to do with congruencies. In the next section, we're going to do a lot with congruencies, so we're kind of leading up to that. All right, so I want to show that dividing both sides of a congruence by an integer does not always produce a valid congruence. All right, so remember, a congruence is A is congruent to B mod M if M divides into A minus B, or if the remainder of A divided by M is the same as the remainder of B divided by M. Okay, so that's what a congruency is. All right, so let's look at an example. So I have 12 is congruent to 15 mod 3. Okay, so this congruency is true because 3 divides into 12 minus 15. Okay, 3 divides into negative 3. Okay, so this holds true. Now, if I divide everything by 3, I'm going to get 4 is congruent with 5 mod 3. Okay, so this is a question mark. We don't know if that's true. Basically, we want to check. All right, so let's write this nicer. And this is not true, right? because 3 does not divide into 4 minus 5. Okay, or another way that you can put it, 4 mod 3 is a remainder of 1 by 5 mod 3 is a remainder of 2. So these are not congruent to each other. Okay, so division for congruencies doesn't always work. Okay, we saw that addition and multiplication worked, right? So in the last section we saw that if I have A is congruent to B mod C, mod M, then if I multiply by C, and C is congruent to D mod M, then AC is BD mod M. So multiplication is good, right? And addition, A plus C is congruent to B plus D mod M. So those rules we proved, but if you can't divide both sides by the same number in most cases, because it will lead us to an incorrect incongruency sometimes. So this theorem shows the special case where we can divide both sides of a congruency. So let's look at what it says. So if M is a positive integer and A and B and C are integers, if AC is congruent to BC mod M, and the GCD of C and M is 1, so basically this number that you're dividing by it was relatively prime with the M, with the mod number, then you can divide both sides of the congruency by that number by C, and you still get a true congruency. Okay, so this is useful to know when you can divide both sides of a congruency. And we can prove this. All right, so if we have AC is congruent to BC mod M, then that means that M is going to divide into AC minus BC, or M is going to divide into A minus B times C, like this. Okay? We also know that the GCD of CM equals 1, so there's no common factors between C and M. So then this previous theorem kicks in. Right here it says that, again, if the GCD of two integers is 1 and A divides in BC, then A is going to divide into C. Okay, so that theorem right here says that because M doesn't divide into C, give me a second. Right. So because M doesn't divide into C, M will divide into A minus B. Okay, well, because A divides into M minus B, that means that A is going to be congruent to B mod M. Okay, so this proves this theorem right here. All right, so I know this section was pretty long, lots of things. We kind of looked at prime numbers. The Euclidean algorithm and the Bezout coefficients are two important methods that we're going to take. We're going to use those calculations in the next section. And some of these sort of side theorems that we sort of learned, like this and the previous one, will also come in handy with the stuff that we're going to do in the next section. Okay, so sort of we're still building up a lot of bits and pieces and some big algorithms like the Euclidean algorithm and finding Bezout coefficients.